Coming was that he would give me 1 hour to speak because I had such a long presentation. If you look at my topic, you can understand what I'm saying. I'm going to derive the universal force and field, and then I'm going to show the experimental evidence that shows that this is superior to all previous attempts for universal force. So that's a lot.
You are in the picture.
Pardon?
You are in the picture.
Oh, I'm in the picture? Well,
Hold on.
can we move that? Oh, maybe that'll help.
You could use
That
remote
better?
control. You can
I don't think it's going to be much better. He's got to stay with that line.
See, I have notes. Unfortunately, I have to see the screen here. Oh, so I'm in your way.
Unless you want to sit.
Would you like to move over?
Charles, get off the podium and sit down in the chair.
Yeah.
Oh, okay, well, I'm a little unhappy with quantum mechanics because it wasn't as physical as they would like. In other words, they had ideas of guiding waves that would allow the particles to act like waves instead of something as mysterious as quantum mechanics has. And they would like to have causality. In quantum mechanics, you don't have the law of cause and effect because it's a probability distribution type of approach. So that is what they did. Oh, okay, I'm sorry. Thank you very much. So I want to show a little video now that demonstrates how we could have guiding waves that are associated with, oops, I gotta go back here. Yeah. Oops, it's not showing me my picture. Let's see, I may have to do it another way here. You don't see it yet. I'm going to move it over to the other screen, but let me get this video started.
So, God bless Bill Gates.
Okay, here we go.
In a world without fences, who needs gates?
I'm making solitons in a swimming pool. You saw he used a plate, and there's two ring toroid solitons. See the guiding waves around the part. The part that's dark is the image of the sun on the bottom of the swimming pool, but it shows the circular shape of it, and you can see the guiding waves around. And I want you to notice that because solitons may be the origin of all elementary particles. And elementary particles will be made of multiple solitons. A soliton is something that has a long lifetime in a fluid or a field, and the lifetime is determined by the strength of the field or the tension in the fluid and the range. In the universe, the longest range force that is strongest is the electromagnetic force. The strong interaction force is stronger, but it is very short range. So it cannot produce long-term solitons. Okay, so that's what I wanted to show there in terms of that video. But notice that he just used a plate. You can do this yourself in a swimming pool, but people have done it like Winston Bostic did it in plasmas. He was the last graduate student of Arthur Compton. He showed and photographed pictures of solitons in plasmas, and he published that as the model for the electron. And that was in the 60s, and the role of solitons in fluids and fields is well established experimentally, and has been, all kinds of experiments have been done. For instance, you can do 2 solitons going through a double slit, or a stream of solitons going through a double slit. You get the interference pattern, and it's due to those guiding waves that you see around it in the field or in the water, in the fluid. So quantum mechanics is not required for the interference effects that we see in experimental results. Now, let me bring this back. I can get it back to the screen, and I can finish going with my presentation here. Okay. So I want to present a solution to the Vigier approach to quantum mechanics. And that solution is that all elementary particles are composed of electromagnetic solitons. That will also imply that the only force in the universe is electromagnetic. The electromagnetic field becomes effectively the ether. There is no particle ether, there's no other type of ether from this approach. And so now I want to review some problems with physics that Lee Smolin at the Perimeter Institute of Theoretical Physics in Canada has pointed out. And some of these problems are, we cannot combine general relativity theory with quantum mechanics. In this work I'm going to do, I will show you the quantization of gravity. We have problems with infinities, electrodynamics, quantum mechanics, and general relativity theory. In this approach, we will eliminate all infinities. We have a problem understanding dark matter and dark energy. In this approach, we'll explain all the phenomena for which dark matter and dark energy were proposed to rescue general relativity theory, but we will have no dark matter and no dark energy. The standard models of elementary particles have 20 to 29 empirically determined constants, adjustable constants, fudge factors, whatever you want to call them, in order to try and explain the different forces in particles in the standard model. This approach has 0 adjustable constants and parameters and explains more elementary particle data than the standard model currently can. Also, the problem that Smolin pointed out is that string theory is not experimentally falsifiable. And the last thing he said that I want to emphasize is that the ultimate problem in physics appears to be the discovery of the true universal force. Now, I want to give some arguments for meta theory to show what we should have been doing in science in the last 150 years. If you're not familiar with meta theory is the theory of theories. It is based on logic and theorems that are proved from logic. The founder of this field was Henri Poincaré, and these fields or these theorems are something that I was never exposed to in obtaining all my degrees in theoretical physics, and so I assume you may not have that experience either. The first theorem for meta theory that I want to talk about is that no two fundamental theories in nature can employ the same fundamental constants, such as c, the velocity of light. Well, we have 4 pillars of modern science: electrodynamics, special relativity theory, quantum mechanics, and general relativity theory, and they all involve c. According to this argument, only one of those can be a fundamental theory. The others are false. They may agree with data, but they cannot be a legitimate fundamental theory.
Why can't they be redundant?
There's no redundancy allowed in fundamental theories.
So why can't all 4 be wrong?
So anyway,
The first 2 are redundant.
Henri Poincaré is the one who first proved this, and that's published in his works if you get a copy of that. And what he said was, I believe that all of these, the results here on these pillars are really electrodynamics. And if we had done electrodynamics properly, we would not need special relativity theory, quantum mechanics, or general relativity theory. And as a result of that, neither he nor Einstein ever received any award for special relativity, which they were the co-inventors of, or general relativity. Einstein did receive a Nobel Prize for his wife's work on the photoelectric effect, but not for special or general relativity. So these arguments were taken very strongly in science at the beginning of the 20th century. And we just ignore them today. The second thing from meta-theory is only fundamental theories can be true theories. All other theories are approximations. They're not true. A third argument is that no two fundamental forces can have the same mathematical form. So if the force of gravity is a 1 over r squared force and the electromagnetic force is a 1 over r squared force, they cannot both be fundamental true theories. From the previous argument, one would say, oh well, since general relativity theory involves C and stuff like that, it's very likely that the electromagnetic force could be the fundamental force. The fourth argument from meta-theory is that according to the superposition principle in meta-theory, not the way you've studied it in your classes, a set of theories describing the universe cannot be logically consistent and physically stable unless it consists of only linear theories or one nonlinear theory. Now let's look at our pillars of modern science again. Electrodynamics is not 1 over r squared, that's nonlinear. The gravitational force in the non-relativistic limit at least is a 1 over r squared force, that's nonlinear. The Schrodinger equation has del squared in it, although you can say that psi is a linear superposition of states. So that might be a mixed bag there. And relativity theory is nonlinear in that it goes as v squared over c squared. So, what do the arguments for meta-theory say? Well, they have to all be linear or one nonlinear theory. Well, all of them except for perhaps quantum mechanics are definitely nonlinear. They cannot be combined with quantum mechanics. You can't combine a nonlinear theory with a linear theory. That will not produce a logically consistent or stable system. So, on the basis of all of these four arguments, and by the way, there are many more theorems in meta-theory than that, on the basis of those, one would say either all of our theories in physics are not fundamental, we haven't discovered the fundamental theory yet, or we could say that with Poincaré, if we did electrodynamics better, we wouldn't need quantum mechanics, we wouldn't need a theory of gravity, we wouldn't need relativity theory. I'm assuming that that is the case. So the question is, how can you do electrodynamics better than Maxwell did? We'll look at that question. Turns out that we've known the answer for 300 or 400 years, but we've ignored it. It's in a book by Isaac Newton called Mathematical Principles of Natural Philosophy. And he said that what you should do in each field of physics is you should perform experiments and set down the results you find in specific terms and precise mathematical laws so that you had as accurate a prescription as you could of what you saw experimentally. Then you should use those, a complete set of those, as axioms and derive a more general form of that force law for that field. And then you should try and predict additional phenomena from that force law to verify it. And do this process over and over in each field, and then see if you can't, from one field, predict the results in another field. So we're going to do electrodynamics following this rule, and see if we cannot predict all the results of related to gravity, the force of inertia, and see if we cannot describe all atoms, elementary particles, nuclei, molecules, origin of life, all those things from this approach. If we look at the empirical laws of electrodynamics, which I've shown here, there's Ampere's law, Faraday's law, Gauss's electrostatic law, Gauss's magnetostatic law, Lenz's law, and the Lorentz force law. We have 6 empirical laws. The question is, how many of these did Maxwell use? The answer is 4. He used 4 of the 6. What did Newton say he should have done? He should have used the full set, not a partial set. So how do we do that? Well, first of all, Maxwell also used a number of idealizations. And I'm going to show some results first. We're going to remove those idealizations, and I want you to help identify them for you. The first one is Robert Hofstadter, doing electron scattering, was able to measure the size, the shape, and the internal structure of elementary particles. In particular, he got a Nobel Prize for doing the proton and the neutron. If you look at these, you will discover, see where I put my thing, you'll discover that there are 3 substructures in these particles. You can see it best on the neutron here. You see you've got a peak, positive peak of charge here, negative peak of charge here, and a positive peak of charge here. And you've got a radius of 2.5 Fermis, or 10 to the minus 13 centimeters. So Maxwell's equations involve point particle idealization. That is not true. And by the way, I've done similar experiments on kaons and pions and muons, and they all have a finite size and internal structure. The second thing I want to bring to your attention is some work of William Hooper at the University of California at Berkeley. He did a whole series of experiments on electric and magnetic fields. In particular, he identified 3 types of electric fields and 3 types of magnetic fields, and he measured 14 different properties of each of these fields. Those fields for the electric field are the static field, the time-dependent field, according to Ampere's law, or Faraday's law rather, and the velocity-dependent field defined by Lenz's law. And to give you an example of some of those, the static field and the time-dependent field can be shielded, but the velocity-dependent field cannot. There's something that was missed at the time, it wasn't known at the time of Maxwell, and it has never been corrected in electrodynamics. So you must take into account these 3 fields separate. And remember that since they have different properties, they do not obey the linear superposition principle because they have different properties. They're unique. The second experiment I want to talk about is the Michelson-Morley experiment of 1886. This is not the famous Michelson-Morley experiment to detect the ether of 1887. This is where they're putting light beams through a flow of water. They have a light beam going around this circle one way, parallel to the flow, and one is opposite to the flow. And then they measure the effect of the velocity on the velocity of light. At the time they did that, it did not agree with Galilean relativity theory. Didn't agree with any theory as far as I knew. In 1905, when Einstein published his special theory of relativity, he showed he could predict the results of this experiment, and it was in agreement with special relativity theory. Then, unfortunately for Einstein, Ewald in 1912 and Osteen in 1916 independently discovered the extinction effect, whereby light is absorbed by atoms in all media, including the vacuum of outer space, and then re-emitted. And there is a path length for which the extinction effect is valid. In optical glass, it's 10 to the minus 6 centimeters, a micron. In air, it's a millimeter, and in outer space, it's a couple parsecs. So that gives you an idea of the scale where you have to take this into account. It was not taken into account in the Michelson-Morley experiment, but Fox did it in 1962, and Renshaw did it much more elaborately in 1996, and this is the result of their work. The special theory of relativity, which says that C prime equals C in all inertial reference frames, is not experimentally valid. The Galilean relativity, the C prime equals C plus or minus V, is, and this is the only experiment that has ever measured that. And so we need to take that into account. So now, how are we going to do the solution? Here are the equations of electrodynamics, the 6 empirical equations. This is the number of unknowns. We have 6 empirical equations, but we've got 8 unknowns. What are the 2 that we don't know? R prime and T prime. What are we going to use? The Galilean relativity, not special relativity. So what do? What's the solution? You just solve by substitution. It's very simple. By the way, in my book, which is over here, I published all of this step by step. I received the award of Physicist of the Year for 2013 from 5 international scientific organizations for publication of this book. But I think most of you are very familiar with it. I have some extra copies here for sale if you'd like some at a discount for this conference. And so, what happens when we do solve them simultaneously? The first thing to notice is, what do we get for Lenz's law? Does that look familiar to anybody? Does that look like special relativity theory? Did we use special relativity theory? No. We used Galilean relativity theory. This comes from Lenz's law. And what it says is that if we have a particle that's moving at a certain velocity, it is contracted in shape, its fields are changed, and guess what? When we look at the results, a constant velocity, this is the force we obtain from this simultaneous solution of these equations. This is identical, 100%, with the force at constant velocity from Maxwell's equations with special relativity theory. But there's a difference. The 2 theories produce the same equation, but the difference is this equation conserves energy and momentum, which Maxwell's equations do not, because they do not include Lenz's law, which enables you to conserve energy and momentum for velocity situations related to induction. And so we can define the energy potential. There it is. You cannot define this with the solution to Maxwell's equations. You can only define the vector potential, which is a non-physical potential. It is not unique. You cannot have a physical potential if it is not unique. This is unique. So what do we see if we look at the normal procedure? We use vector and scalar potentials, and this is the same equation we get. Now I wrote this in terms of vectors, but it could be just v squared over c squared sine squared theta, which might be a more familiar form to you. So anyway, this is a different theory based on things that are not physical, things that people objected to at the time of Maxwell when Heaviside and others introduced this nomenclature and this approach. And you look historically, you can see quite a few people complained about that in Great Britain. from other parts of the world. Now, what I want to do is to show you what is going to be the difference. They look identical at constant velocity. But if I have a energy potential, I have a relationship for the energy potential which says the derivative of the energy potential with respect to time is equal to minus the force in terms of r, v, and a, the acceleration, dot v, for a constant force. So now for a constant force, I can find two more terms to the electromagnetic force law. Are those terms going to be in Maxwell's equations approach? No, they're not allowed. So, do these exist? Well, we're going to find out they do. Besides those two terms, I can calculate the power radiated and get the radiation reaction force from this approach to electrodynamics. And when I do that, I get three terms following this procedure. And two of them depend on boundary conditions, and the third one is going to be there regardless of the boundary conditions. It turns out that experimentally in accelerators and those type places where I've worked for a long time, the radiative reaction force is equal to the third term. So I've got to have the first and second term somehow go to zero. And in order to make that, I have to have certain conditions. And it turns out the condition that will allow these to go to zero is that all elementary particles have to be constructed of periodic closed toroidal rings. And so those happen to correspond to solitons in the electromagnetic field. So basically, from this derivation of this force, we have a key to the structure and the nature of all elementary particles. They have to consist of closed charge rings or solitons in the electromagnetic field, and they can have more than one in an elementary particle. So it turns out that to get the structure of all the elementary particles, you use combinatorial geometry, and you ask what are all the stable structures that can be formed from these closed toroidal rings. They're going to have magnetic moments, they're going to have spin, they're going to have charge. You've got to use all of your force laws in order to find what the equilibrium arrangement of these rings are, and lo and behold, you can now predict the properties of all the observed elementary particles where you can form the particles into a beam and form experiments, and you know for sure they exist. All the others are hypothesized.
What is your gamma?
Gamma here is 1 minus v squared over c squared. Yeah, I'm sorry. It doesn't come from special relativity theory, it came from the general form. So here's a picture, for instance, of the electron. It has 3 of these toroidal rings. This is what a toroidal ring looks like if you look at it more closely under the microscope. It has is basically a fiber, but instead of going in a perfect circle, it looks like it's something that goes around on the surface of a toroidal ring. This approach enables you to define Planck's constant and to predict the value. Quantum mechanics cannot do that. Quantum mechanics cannot tell you from fundamental theory what the value of Planck's constant is. And here it is. When you do the balance of forces in one ring, this is the expression. Planck's constant equals E squared over 2 pi epsilon naught c times the log of 8r over r, where the r, the big R, is the radius from the center to the outermost part of the ring, and the small r is the cross-sectional radius. So, now what happens? We are able to predict, I don't know if you realize this or not, but you cannot predict the radiation reaction properly in a consistent way from special relativity theory and Maxwell's equations. My son went to Caltech, and they held 2 international conferences in this century after the year 2000, and they were unable to achieve the resolution of this problem, even though they tried. And the problem is that special relativity theory and Maxwell's equations produce forces that only depend on R and V. And you've got, if you're going to describe radiation, you're going to have to include acceleration and dAdt, and they don't include that. And so they have a great problem of being able to reach that. Now, suppose we have done that, we've obtained our force. Now, there's some things that physicists have not paid attention to, that chemists have. And one of those things is that there are multipoles. And there's a hierarchy of electromagnetic interactions related to the multipoles. Here is two charges interacting with a Coulomb force in the traditional diagram. This is a single charge interacting with a vibrating neutral electric dipole, where it has an amplitude of vibration A and a frequency omega. And this is going to produce the inertial force, we're going to find out. And then the second one we want to look at is the interaction of two vibrating neutral electric dipoles, and it's going to produce the gravitational force and allow us, these two results, to define for the first time in the history of science what is inertial mass. It's not a fundamental property anymore. It's an electromagnetic property of elementary particles, and the gravitational mass will again be an electromagnetic property, and we can derive big G. Can any other theory of gravity derive and predict the value of big G without using any experimental data? No. So, let's go and look at the case of inertia. Here is our example. Here I've drawn the electron is the big ring, and the proton is the small ring, and this is the amplitude vibrating back and forth. And because we normally think of the proton as being much heavier than the electron, I'm showing most of the amplitude of vibration is due to the motion of the electron. And so if we do that, and it's calculated step by step, took a whole chapter in this book, you get the force of gravity. What do we get? Surprise. We get, I mean not the force of gravity, the force of inertia. We get this is the actual results we get. We get a term proportional to the acceleration, and we get a term proportional to R cross A. Have you ever seen the force of inertia written in terms of that? No. Here's what we get if you write it in terms of mass terms. You see we get MA, that's what we would expect, but we get this second term. This second term has never been predicted by any previous theory of inertia, and we're going to see that we have experimental evidence that's quite remarkable. It looks like a magic trick that shows the existence of this term. But what is the evidence?
Question?
Yes.
Isn't your last term there R cross A equivalent to a Lorentz force R cross F? Or would you say that R cross A in parentheses is something else? I wanted to call your attention to Bernard Niche's work.
Remember, we're working with the basic parameters in electrodynamics. So this force of inertia is a subset of the full electromagnetic force. Electromagnetic force is going to consist of force of inertia, the gravitational force, and the Coulomb force, and other things that we haven't identified in the past.
I'm just trying to reduce that last term that you're subtracting there to something that...
I'm not subtracting it, that's what you actually derive. I'm just writing it in the notation that corresponds to what we're used to seeing for the inertial force. In other words, you could change the notation, but if I keep the same definition here for the inertial mass, and I keep the vector dependence there, then I will get, this will be the coefficient. So now, what kind of evidence do we have that this prediction of the improved electrodynamic force is producing a proper theory of inertia? going to show that there are three types of data here. The vibrating neutral electric dipoles that give rise to the inertial mass also give rise to the 2.7 degree Kelvin cosmic background radiation, and they predict perfectly the data that we have taken. Well, you'll see that in a second. The second, conservation of energy plus decay of inertial mass plus Mach's principle, which I don't have time to go into, but it's in this book, a whole chapter on that, shows how to predict the velocity of the arms of spiral galaxies to exceed the Newtonian predicted values and to be exactly what is observed. So this approach with the definition of mass, inertial mass, and Mach's principle enables you to not have to have dark matter or dark energy. And then the third thing is the non-radial term, the second term we get, which has never been in the force of inertia, enables us to explain some experiments of Eric Lathwaite, and I'm going to show a video of that, which will show some of the stuff. You'll think he's a magician when you see this, because it doesn't, our minds think like Newton's laws, and we just don't think that's possible. Okay, here is the fit to the data for the cosmic background radiation. The red dots is the prediction, I guess you would say, for the temperature 2.74 degrees. This has to do with the vibration of the neutral electric dipole in, say, hydrogen. Most of this data here is due to hydrogen, a little bit's due to helium. So anyway, that is predicted. It doesn't have anything to do with cosmology, Big Bang. It just has to do with the decay, actually, of the force of inertia over time. This is the data, the blue dots here, for the particular spiral galaxy NGC 6946, but it's similar for quite a few galaxies. I'll just put one up on the slide. The green line is the prediction of Newtonian and general relativity theory. So in order to get general relativity theory to predict something closer to this, they had to make up dark matter. But we predict a modified Newtonian dynamics. This is predicted, not a fit. This is the predicted value. So the yellow line. And we predict many other things based on this that are astronomically verified. I'll show a couple of them. This is the Tully-Fisher galactic luminosity, and the luminosity is proportional to V to the 4th power. We predict that. General relativity theory does not predict that. We predict that. But not only do we predict that, we also predict, this is the velocity versus R in terms of the size of galaxies. And you see we're able to predict 900 of these that were measured. We also are able to predict, if we look at the frequency of the various luminosity, that we are able to predict that there's a quantization in the frequencies that are seen from various galaxies. And this quantization, we're going to show more about it, but it's a reflection of Bode's law. And we'll see that more about that in a few minutes. Let's see if I can do this next one here. This is an experiment I want to show you. If it'll come up. Oops, it's not coming up. We have to, it's, I don't know why the video's not showing you. Just a second, I want to go back to it. I'm going to get it started and then I'll put it on the screen. Oops, not doing it.
Why are you doing that, Charles? You said you predict
And you see these calculations somewhere in the data that you use?
Pardon?
You often say we predict. Can you see the data and the calculations?
It's in my book. I can't,
Is
you don't
all
have
the data
time.
in there?
It's all in there, yeah. And, but I was not the first one to show this modified Newtonian dynamics. An Israeli scientist did it before me, but he didn't know the origin of the effect. He just said, empirically, we see this. And he even gave the empirical parameters, which we predict from scratch. So it was interesting that he noticed that all of these relationships, but he didn't know why. We predicted, we tell him the reason why. And so it was very good. I'm not going to be able to show this apparently. Let me see.
Is it the aircraft video?
Yes.
Sure,
Yeah. I'm trying. Just try one more time here. Okay, now we're going to get it.
This is an experiment with a spinning wheel, a rather large wheel, 13 inches diameter, mounted in a ball bearing on a shaft 3 feet long. I'm going to hold it like this and swing it in a circle and lift it with one hand, but only when it's spinning. First of all, let me weigh it to show you just how heavy it is.
This, by the way, is on the internet, and many people have reproduced this
It's
experiment.
quite an effort. It weighs
Yeah, but it's
about
quite
40
logical.
pounds, and I can't lift it any
All
higher
this
than that
makes it
Pardon?
without a lot of
quite
strain.
fancy afterwards. There's nothing fancy about it.
So now
It's more impressive when
we'll
the
spin
10-year-old.
it up to
Yeah,
2,500 revs a minute,
10-year-old.
when it becomes a live thing. Then I shall lift it 5 feet in 3 seconds by going round in a big circle. Whilst I'm doing it, I shall talk to you so that you can tell from my voice that I'm not under any stress of any kind. And the minute I shall let go with my left hand, and holding this remote end of the shaft only, I shall lift the wheel through 5 feet, all on its own, with no effort on my part. All I do is apparently just to steer it along the path that it's already decided it would like to go. Then there's the question of how you stop the wheel.
By the way, he did this before the Royal Society of London, and he was the first person to have his membership canceled for that, including all government contracts.
Did you notice that as it went round in the circle, there was no centrifugal force trying to pull my arm out sideways? Let's just do it once more. To save time, we've already spun it up. So here goes 40 pounds of wheel as light as a feather. This is not a conjuring trick. This is a fact of science. Watch it again carefully. The fact about the spinning wheel, so far, everyone has missed.
Okay, so the reason why Eric Lathwaite, who was the inventor of the high-speed electric railroad, which was originally supposed to be installed in Great Britain, but where is it? It's in Japan, China, and Germany, but not in Great Britain. And this is the one that goes very high speed. All of those were taken away from him because that experiment violates Newton's law and the analysis that you would do for a gyroscope. And when people realized that, Newton was a very important person. You can't besmirch his name. And so they canceled all that. They took extreme measures in Great Britain. The British are not going to let them do that. Don't blame them. They're not to be singled out. But anyway, that's the reaction that they had at the time.
5 minutes.
Okay, now I want to do the force of gravity. And so this is the general, whoops, show it there again. This is the general slide. This is the result that we obtained. You see again, this is the result. This is the result up here. There are two terms like there were before. And the first term, if you define mass using these type of terms, you will get minus g, mg1, mg2. The second term goes as r dot beta, which is v over c, times r cross beta. This is a new term that has never been in any previous force of gravity as far as I can tell. It produces a corkscrew spiral motion. Now, what kind of data do we have to confirm this theory of gravity? The first thing is we again have vibrating dipoles, and they're going to produce the 2.7 degree constant background radiation. We have the constant background radiation. When it's emitted, some of it is reabsorbed, but some escapes, causing the force of gravity to decline or decay. G is not going to decay, M is going to decay. This causes the Earth to expand due to the declining force of gravity. It causes the angular rate of rotation of the Earth to slow. It causes the Earth's magnetic field to decay. It causes the moon to recede from the Earth. And we already knew that gravity causes a redshift, but if gravity is decaying and we look out at distant galaxies, we're seeing what the redshift from a time when gravity was much stronger. And so the Hubble's redshift law is now explained by the decay of gravity. And the non-radial term causes the tilts of the orbits of the planets with respect to the equatorial plane of the sun. It causes the quantization of the planetary orbits, known as the modern version of Bode's law by Stanley Dermot, a British person, by the way, and the quantization of all galaxy redshifts. So we're going to look at that data. I think that's about as far as we're going to get in this presentation. Oh, here's the first piece of data. This is the official U.S. Navy map of the bottom of the oceans, showing the expansion of the continents. It started here in the Dead Sea, went down the Red Sea, split, formed the Atlantic Ocean, the Pacific Ocean. It shows a three-dimensional expansion of the Earth. Here is a close-up of that data. These stretch marks are not trivial. They are mountain ranges under the ocean. They're not trivial. These structures are bigger than all the continents put together. 6/7 of the surface of the Earth is these stretch marks. The Earth has expanded 70% in recent times. Here is another form of data. This is again U.S. Navy data. They took a magnetometer, put it behind all their Navy ships. They measured the magnetic field. Here is the Mid-Atlantic Ridge. Notice the parallelization of different strengths of stripes on each side of the Mid-Atlantic Ridge. This shows you a cross-section of the stripes. Notice the width is changing, showing that the expansion of the Earth is declining due to the 1/r³ factor in terms of the rate of expansion. And you can see that the expansion has only been apart, never running into one another or something like that. Here is the plate tectonics data. Notice when you have the two arrows pointing away from each other, that's a three-dimensional expansion. You see it in the Atlantic Ocean, you see it here You see it over here. All the Earth has been expanding three-dimensionally, and I don't have time to show it, but you can show that has occurred in the last 6,000 to 12,000 years. The 70% expansion in the radius of the Earth. That is not explained by any other theory of gravity. And by the way, it's not just due to our planet. The moon shows the same thing. Mars shows it. The moons of Jupiter, and they're amazing. I have one little video I'll show you, and I'll close with that. Well, maybe I'll skip that.
Yeah, I want to see the 70%.
You want to see this? Okay. Let's see. I gotta. Let me get it started. Oops.
What about the subduction zone?
Yeah,
There are no such things as subduction zones. You'll see that in the movie here.
I think we watch it.
Come to the earth, which
Okay,
fell,
now.
we get here, the way it is now. Here's our world, our planet Earth floating in space. We will be going backwards.
Oh, wait a minute. I had it.
Very distant manner. Notice there is no subduction, no rotation of tectonic plates, no twisting, no form fitting, no altering shapes or sizes. It would be impossible for these continental plates to fit together perfectly without this being true, and yet the upper tectonic plates fit together perfectly on a much smaller plane. Yes, there's been some erosion, landslides, blah, blah, but overall, this activity is insignificant. There is a kind of conspiracy of silence among certain scientists. They know, but are not telling you, that the upper tectonic plates of Earth also join in the Pacific. Not partially, they join totally. You are asked to believe that the continents swim or drift about willy-nilly, bumping and crashing as if they were on a grease skillet. This is not true. The simple truth is apparently too upsetting for too many apple carts. We're now going forward in time to show how the actual growth of the Earth took place. Imperfect as the details, but the overall is nailed. Antarctica, as you see, has become subtropical. Africa, on a smaller globe, moved way downward under the globe. In fact, for hundreds of millions of years, the bottom of Africa was the South Pole. South America's tail goes under and wraps around the bottom of Africa, then incredibly joins coast with Antarctica. 65 million years ago and more, these continents were joined, and marsupials like the duck-billed platypus roamed from Australia, Antarctica, and across southern South America and up into Africa. The platypus. Dinosaurs roamed all over this world on the upper tectonic plate because there were no oceans, just shallow seas. Here today, Antarctica is frozen over, and Australia and its surrounding islands are the remaining home of marsupials. Do you see how broadly the Pacific is opening compared to the Atlantic? This is exactly why the knee-jerk Pangea theory exists. The Pacific spread is too difficult to easily visualize because it's so big. The Atlantic spread is so obvious that a child would recognize it, but they are the same.
By the way, Neil Adams is the person who makes the Batman and Superman cartoons, and he's using the cartoon capability to show the expansion. He's done it for many other objects, the moon, for some of the moons of Jupiter, and also for Mars. And it's amazing how well it is able to predict the data. Let me just show these couple more slides. This shows the tilt of the plane of the orbits with respect to equatorial plane of the sun. And notice, if you look at this one, and then this is double that, and this is triple that, and then this is fine structure in here. So we've got a number of things that we can explain. Neither Einstein's general theory of relativity nor Newton's universal law of gravitation can explain the tilt of the orbits of the planets. But that's not all. There is a man named Bode who lived at the time of Newton, who measured the quantization of the orbits of the planets, and then he did it in terms of fractions, but this fellow, Stanley Dermott, in the 1960s did it using this equation, where Pn is the period of the nth planet or nth object, P naught is the period of the sun, and A is the semi-major axis to the nth power, and there is the result of the prediction of that for our solar system. And what you see is that, yes, it's very good fit to the data. And what is that predicted by? That second term in our force of gravity. And it's not just the planets. Here is just one case. This is the moons of Uranus, and you see that they also lie on a straight line, including the planet. And so it turns out Jupiter's the same way, and Saturn, which have a lot of moons, so you can see this effect nicely. So that is not possible to be explained by these previous theories of gravity. Now, the Hubble redshift, as you know, the farther away, the more the redshift that Hubble measured. And the Hubble relationship is a linear relationship with respect to distance. And people thought that was a Doppler shift, but then a fellow named Houghton Arp started finding all these galaxies like NGC 4319 that have a, what do you call that, smaller entity that's attached to it. And it, pardon?
Satellite galaxy.
No, these are, wait a minute.
Quasars?
Just a second, I'll look at my notes. Quasars, these are quasars.
Quasars.
These are quasars that are attached to this. Quasars are much younger than the rest of a galaxy. And what you see, look at the redshift here. Z is 0.006, and the redshift of this piece of the galaxy is 0.07. Doppler shift cannot explain how these two could remain together at all. This is a huge difference in the velocity. And so the notion that the Doppler shift can explain Hubble's redshifts is not true. The deviations from the straight line may be due to Doppler shifts, but the general thrust is due to the gravitational redshift.
Gonna have to stop now, way over time.
Okay.
If you want to have a couple of questions, coffee break, next talk, let's vote.
If you would like a copy of my book, my wife has some over there, and they're $15.
How many?
Copies?
How many dollars?
15.
Wonderful.
What's the vote? No voting.
In your
No good at voting.
gravity law that you had there, I didn't see the term for the position of the perihelion of Mercury. How do you account for that?
I'm sorry, I didn't have time to go into that, but it's not in my book either, it's in separate papers.
Can you pass that to me, please? I would like to see it.
Okay, it has been done by other people, not just me.
No, but I want to see how you do it in your,
Yes.
context.
Right.
I have a quick comment. Have you ever studied the blue shifted objects? Have you studied the blue shifted objects?
Yes, they can be a Doppler shift also to the other direction. Well, I didn't get to finish, but let me show you this. These are all the red shifts in the world that we have been able to measure so far. This is from the position of the Earth, which is, according to the cosmic microwave background radiation, we are about 2 million light years from the center of the universe. If you plot those same data from the number of redshifts from the center, you'll see you get 5 peaks. They obey Bode's law, and this shows that all of the galaxies that are in our observable universe are in rings about the center of the universe, and they are at quantized distances, the rings are, just like our planets are at quantized distances from the sun.
All right, we're gonna have a short coffee break. Maybe bring your coffee in here so we can
Hey.
start.